Ohayou gozaimasu. Unfortunately, that is the limit of my Japanese for this morning. I would very much like to thank Jeff-san, as well as the rest of the ROSCon JP organizers. Speaking as one of the co-organizers for the main ROSCon, it has been very inspiring to see groups like this emerge around the world. This is I believe, the 9th ROSCon that I have attended, this one here. I would like, as my talk right now, I will be talking about making autonomous robots and robot vehicles safely. It is important for us to put robots out in as many places as we possibly can, and safety is a key part of this. To introduce myself a bit, in 2005, I started my career working in equipment engineering at Honda of Canada to help with building the assembly line. In 2007, I was one of the first interns at Kiva Systems, which is now known as Amazon Robotics. There were only 30 of us at the time, and they only had one site active. This is where I started experiencing the potential of autonomous robots. I then moved to be an early employee of a drone startup. And then from there, in 2009, I was co-founder of ClearPath Robotics. In 2010, ROS became more and more popular, or started to get more popular. ClearPath became the first for-profit company to support ROS, so right after Willow Garage. And then in 2012, the first ROSCon happened. As well, we also joined the founding board of directors for the Open Source Robotics Foundation, which is now known as Open Robotics. And we still work to support Open Robotics to this day. In 2014, we started getting into building industrial robot vehicles with our Auto Motors division. This division pioneers using self-driving vehicles and robot vehicles in factories and warehouses. And here now, in 2019, our major push of our company is in international expansion. We are expanding into Western Europe and Japan this year. As you can imagine, this is over 10 years of experience building autonomous vehicles to work safely around people. And I thought it might be helpful to share some of our learnings, some of which were very expensive learnings, with everyone in this audience, because it's important to have as many companies and as many team members and as many people as possible working to build safe and efficient and productive autonomous vehicles and robot vehicles for the world. There are 8 steps. I'll go through them one by one. The first step is first understanding what is safety. Safety does not mean perfectly polite vehicles. It does not mean vehicles that do not ever touch other objects or other people in the environment. It depends. If you have a robot which is meant to go through a train station around people, it probably has to come into contact with people or it will get nowhere. And here you see pictures of human-driven vehicles and vehicles themselves which are dented, which are damaged, or damage that they cause to the environment. Zero risk is impossible if you want robot vehicles and robots to work in our environment. But what is important is keeping people free from harm. This is what is important. This is safety. Harm can come in a few different forms. There can be direct harm, where you have the robot coming in contact with the person and hurting the person. But also important is indirect harm. If your robot or your robot vehicle collapses a shelf on top of a person, that is equally unsafe. And these are contingencies which must be considered as you're developing your systems. A good way to think about this is as the safety increases, you usually need to either decrease the speeds or increase the space required around your robot. One of these two things usually has to happen. And if that isn't challenging enough, it is important that the robots are always safer than people performing the same task. We as society, every country around the world expects robots and machines to be safer than people. It may not be fair, but this is the world that we live in. So if your only goal is to be just as safe as a person, whether you are building a forklift or a self-driving car or a delivery robot, the world will not accept it. You must be much safer. Another challenge which comes into play is that there are no more machine operators. Traditionally, when you build industrial equipment, there's a machine operator at the equipment, as you see on the left. They are highly trained to operate that machine safely. And you can trust that they'll operate the machine safely, and they will know what to do and what not to do. Machines have operators. But robot vehicles, they have bystanders. Anyone around that robot might need to or will need to be safe around the robot. And what this means is that it's no longer possible to train everybody to be safe around the robot. If I want to put a robot in this room, I need to make sure that it is safe and not to make sure that every one of you has to fill out a checklist or follow training just for me to put a robot in this room. It's very important to know who these bystanders are as well. On the right, we have two individuals behind one of our auto vehicles. They are working in a factory. These are factory bystanders. They're adults. They know about equipment. They are wearing boots, steel-toe boots, and overalls. But not every robot is being deployed in a factory. It's important to ask, who are your bystanders first? Are they factory workers? Factory workers are adults. They're wearing boots, as we said. They're wearing clothing. On the other hand, you may have, on the top right, a sidewalk delivery robot, a robot which is designed to deliver goods through the city. Here, your bystanders may be children. They may not be paying attention. Or on the lower image, we have an airport robot. Your bystanders here, they're probably stressed. They're probably not paying attention to the robot. They have other things to think about. They've just missed their flight. You can't expect them to know and pay attention to everything going on. And it's important to understand this. Part of that, the key point is, how big are they? This is important to know if they are going to be harmed by the robot. A child is much more likely to be harmed than a fully grown adult. An adult is more likely to respect the robot as another organization's property or another person's property than a child is, and the adult will not touch it. The child will. There is the matter of what clothing they may be wearing. Again, are they wearing any protective clothing right now, or are they walking around in bare feet? And finally, it's the question of how foolish your bystanders may be. When you are in a factory, people respect that there is heavy equipment being operated. When you are in a city, in a park, people do not expect heavy equipment to be operated. They are more casual. They may be more foolish around this equipment. As you're building your vehicles, as you're building your products, it's important to ask yourself this question. And in some ways, if you have that choice of putting your products into a space like a factory, or putting your environment, or putting your products into a space like a school, the factory will give you more freedom to test and deploy your products. because you don't need to worry as much about some of these concerns. Now, at this point, you might say there are standards for all of this. We can use the standards. In some ways, that is true. But we are creating the future right now, and the standards are not always caught up. To give some background on standards for those of you who may not be familiar, I know I was not when we started. There are 3 types of main standards. The first is type A standards. These are general principles of design. These are good practice no matter what you are doing, no matter what industry you are in. There are type B standards, which are generic standards for a industry. There may be standards which cover all automotive industry or all factory or all hospital. And then type C standards. This is specific machinery. For example, you will have a different standard for an autonomous cart in a factory than a conveyor in the factory, and a third standard for a robot arm in that factory. And then tying all of this together are national standards. Countries may decide to make one or more of these standards mandatory at the country level. I'll provide some examples here. These are very relevant examples, and some of you may be familiar with them. The country standards, of course, you have standards like CE for Europe, you have JIS for Japan, or CSA for Canada. And then in this pyramid here, a type A standard that we use is ISO 12100. This is a risk assessment standard. It provides standards on how to do risk assessments. Then we can go further into a type B standard. In the industrial use cases, you have ISO 13849 that talks about safety systems, and IEC 61508, which talks about functional safety. These are specific to factories, but there are many times these standards will be equivalent to other industries. For example, there's another standard called ISO 26262. This is an automotive standard, which is very, very similar to IEC 61508. Many times, standards agencies copy other standards just so they can make more money by selling them. And then at this type C standards, which are very, some of these are very new, and these are all related to robots here. There is ANSI B565. This is a standard for the older style of automated guided vehicles or automated guided carts, AGV or AGC. Now we have a new standard which is being developed right now to take into account that technology is progressing, which is RIA R1508. And there are some other similar standards. For example, we know that personal care robots are a very, very important topic in many countries around the world. So there is ISO 13482 under development for personal care robots. So here you can see that if you want to do just a risk assessment, you can look at type A, but then you can get more detail to say building a functional safety system is a type B standard. But then finally, if what you really care about is just building a personal care robot, you can start with this one down at the bottom because people have already done the rest of your work for you. Unfortunately for all of us, most of the Type C standards are still in progress. This means that when you are building a new technology, you can't always rely on these Type C standards existing that help you guide your way. They should have advice on topics like moving object detection or 3D object detection, how to test your vehicle dynamics, how to use machine learning in a safe way. This is the sort of topic which should be in these standards, but because the standards aren't written yet, we need to do something different. If you're building a new piece of technology so new that the standards groups have not yet caught up, then you start with these type A and type B standards. It takes time, but this is what we had to do when we started building some new products. There are ways of building, or there is the potential of robots is moving much faster than what the standards bodies and the standards agencies have caught up to yet. I'll just spend a brief amount of time talking about risk assessments, because this is a very important topic. Just so I know, could you raise your hand if you have done a risk assessment before? Okay, a good amount of people. Could you raise your hand if you have heard of a risk assessment? Okay, more people, very good. A risk assessment is a structured way of laying out the various risks, safety risks, your product may cause, and a structured way of guiding your team through removing these risks and proving later that you have removed these risks. You have rows. Each row represents one risk. And then there are columns which make up properties of that risk. There are also sub-rows, which I will speak to. To use one example, if you have there's a first risk. You don't need to understand what it is. I can't read that from here either. But you have one risk, and you notice that the end box is green. That means that the assessment that you've done along the way and any design changes you've made along the way have reduced the risk to acceptable. This is good. But there is another risk where the end box is red. It means that the probability of the risk or the severity of the risk, any of the types of or the impacts of the risk, they are too high to be reduced by a single approach. So you are still red. The risk still exists. Then what you do is you lay out another way of controlling the risk. And now you see we are yellow. And you lay out yet a third way of reducing the risk in your system. We're still yellow. And then you add a fourth way, and now we are green. So as an example, here you may decide that you need to add 3 different safety systems to make your risk acceptable. This gets done for every risk you can talk about. But it is very helpful because it means that people always have the same understanding of the system. That there is no need to worry about some risk that one engineer has talked about and you're not sure if it has been taken into account in the design or not. You can have a master document which lays out all of this detail. This format here also is this ISO 12100, the format or the standard that I referred to before. This means that anyone else who knows ISO 12100, any other company, which is most certification companies, lots of other robotics companies, will know how to go through this format with you. There's also the question of how much time you need to spend looking for risks and what kind of risks you spend looking, or what types of risks you look for. Because there are so many different ways a robot or a robot vehicle interacts with the environment. It's very important to make sure that you are focusing on the right risks to reduce. For example, a low probability, low impact risk is not an issue at all. This is like a robot stubbing your foot, running into your foot. It's low impact, it does not hurt, and it's low probability. It probably isn't going to happen. The robot will see you. maybe over time, these issues happen, but you can handle that via more of a Kaizen initiative after the release of the product. It's not important to focus on. Then there are low impact, high probability issues. So in this example, if you have a robot which is actually running over your toes, your feet on a regular basis, here it's not a safety issue. It is a product quality issue. It is annoying. It is something your customers will care about and provide feedback on. So you do need to fix it, but you don't need to focus on it like a safety issue. You don't need to put as much effort into validating that the fix is there. And the reason for that is because you want to put as much effort in as possible into these high impact lines. Now, high impact, high probability, you might think I would color red because these are major issues. They are high risks that happen a great deal. But the reason I do not color it red is because every engineer can figure out that these risks exist. These risks are very clear to people. When you have a self-driving car on the road, a high probability, high impact risk is a self-driving car hitting somebody. But everyone knows that is a risk. It's important to put into your risk assessment and to mitigate, to minimize, but the real challenges and the real risks to be aware of is high impact, low probability risks. These are the risks which are not obvious. These are the risks which do not stand out in the development process, but can still cause severe harm. This, if you are the person leading the company or leading the development team, here is where to be focused. You can trust that the engineers, the rest of the engineering team can take care of the high impact, high probability risks. But these low probability, high impact risks, this is the challenge. There's a number of mitigations which can be put in place here. There is intrinsic safety, which I will speak to on the next slide. This is best. This is where you don't need to add new control systems or new training at all to your product. There is functional safety. This is where the risk assessments are really used. This is by adding lasers and cameras and other sensors and other control systems to the product. Then you have the option of providing training and awareness. Sometimes this is okay, but it depends on your bystanders. If you are in a factory, this is probably acceptable. You can inform everyone at the factory that there are robots in the factory that they need to watch out for. But if you're at an airport or if you are in a subway station, you can't provide training and awareness to everyone that goes into the subway station. Finally, there is always the option of insisting that people wear protective equipment around your robots. This is an option which should be avoided. To talk about intrinsic safety. Intrinsic safety, if you're a software engineer, intrinsic safety makes your job very easy because you don't need to do any work at all. Intrinsic safety means that when you understand your bystanders, who your bystanders are, you ask yourself this question: can the bystanders beat the robot in a fight? If you have adult bystanders and large bystanders, they can probably subdue a larger robot than if your bystanders are children. And what this means is that if the robot is smaller, then it will not cause any harm to the person, no matter what, because it is too small to crush or to impact or otherwise harm the person. For example, a pepper robot will not harm me at all. There is nothing a pepper robot can do to harm me. But a small child, the pepper robot might be able to harm. So what we would say is that if we are deploying a pepper robot in a factory, the pepper robot is intrinsically safe. But if we are deploying a pepper robot in a school, it may not be intrinsically safe. A good guideline, if you're working around adults, is that if your speed is generally less than 0.3 meters per second, or your total mass is less than 100 kilo, it is probably safe, probably intrinsically safe. If you are well beyond this in either speed, for instance, say 2 meter per second robot, which is common in certain places, or a 1 metric ton robot, then it is very, very unlikely to be intrinsically safe. No matter what, it is also good to understand some key safety basics. Even if you're building a small robot, it is good to start conservative and add some common aspects of safe design. For example, safety-rated laser scanners, like those made by companies like SICK or Hokuyu. Emergency stops, clearly visible emergency stops. Power lockouts, so that when you are servicing the robot, you can guarantee that the power has been removed. Or wireless emergency stops for your initial testing. If the software is not yet done, the safety systems are not yet done, you can have wireless emergency stops just to be sure. This next part is a little bit more detailed. Have any of you heard of ISO 13849? I see 2 or 3 people, 3, 4. Okay. Have any of you heard of the phrase who has heard of the phrase a category 3 or category 4 emergency stop? Roughly the same people. They are very coupled. So what ISO 13849 does is it lays out different kinds of architectures to give guidance on making a safe system. For example, if you have a robot vacuum cleaner, we know this is intrinsically safe. It can fall down the stairs, it can run into people. It is not a risk. So if you want it to stop it from going over the edge of stairs, you might only need one range sensor and then some basic logic and then an output relay. This would be called a category B or category 1 system. Category B is very unreliable. Category 1 is when you use some slightly better parts. It's slightly more reliable. There is math behind this slightly more reliable. If you would like, the math is all in there. If you say that what you're talking about is a larger robot vacuum, is something that may cause a little bit of harm, or you may want it to be a bit more reliable, then you would add some additional logic. You might know, for instance, that sensors don't always produce the same value. And if they do produce the same value, something is wrong. For instance, someone has unplugged the sensor. Or you might say that if from a ROS perspective, if the topic is no longer publishing, there is a problem. So here we might use some other logic. Wherever my mouse is. There it is. We might use some other logic here that says something like, if the ROS topic is no longer publishing, then also trigger the fault. And then there would be another kind of fault there. We would disable the motor controls. Here, this is called a category 2. It is slightly safer, but still not something I would personally trust my own life to. The highest level are these category 3 and category 4, where we have redundant sensors We have redundant processing, 2 different computers usually. And then we also have monitoring of the outputs. So we know that not only does this logic trigger if the ROS topic is no longer publishing, but if this logic triggers and this output does not do its job, then we will also trigger this logic. It's making sure that any one of these points can fail, and number 1, you will still become safe, you will fail safe, and number 2, you will know that something failed. So you can go in and service it as well as making it safe. These are the category 3 and category 4 architectures. And when you are talking about a system that must be safe around people, a large robot that must be safe around people, these are the architectures that you will typically use. Then there's a question which is commonly asked. What about neural networks? We can't understand what is in here. How can we use a neural network? The answer is usually you can't. In this case, if you have a neural network all the way up at the top of your architecture or up the way at the top of your stack, you probably still want safety-rated subsystems down here. Oh, there's my mouse. So here, you could have safety-rated subsystems. And then here, you can have well-tested code, predictable code. And then only up at the top may you want to include neural networks. So that when you if your neural network gets something wrong, you're still able to rely on many different parts below it to first make sure you're safe and also make sure that you understand and are able to predict what is going on. Some of our systems, for example, most of our systems run active production lines. If we have a problem with one of our systems at Toyota, for instance, we are deployed in 2 Toyota plants. If we have a problem with a system at Toyota, the management at Toyota does not want to hear, we can't tell you what went wrong because the neural network was in charge. That is not a good answer. So because of that, we make it very clear that our primary performance and safety is all in systems that we understand. And one of the final points here is statistics. This is quite important because as you go through the math and the guidelines on building safe systems, you realize that when you're designing a robot, it needs to be safe. The time between dangerous failures needs to be millions, if not tens of millions of hours. This is not something that you can put a single robot here and watch it drive around for a week or a month or even a year and say that it is now safe. There is a great deal of statistics involved, and it's important to trust these other subsystems which have already been engineered. For example, trust in the emergency stop systems or safety lasers have statistics like this already published. So they will say things like, you can trust this laser sensor to have this level of performance, this level of safety performance. They will guarantee this. The other way to look at this is what's called mean time to dangerous failure. I believe many people have heard of mean time to failure or mean time between failures. Those are, all failures. Those are failures that maybe are just annoying. Mean time to dangerous failure is the time between failures which can cause harm. And what you can see here, if you look through these statistics, is that the mean time to dangerous failure of your final robot system, if it is not intrinsically safe, needs to be upwards of 10 to the 6 or 10 to the 7 hours. That's 1 million, 10 million hours, in that range. And there's a number of different ways to assess this. ISO 13849 uses these PL numbers, PL A, B, C, D, and E, with E being the highest performance level. And there is another standard, 62061, which uses SIL numbers, safety integrity levels. They all do relate to each other. So there's this table here that shows that they relate to each other. So if you have, for example, a European sensor, they tend to give you SIL numbers. And if you are assessing with ISO 13849, you'll use PL. And there are tables which allow you to combine them. And in the end, what you're looking for, if you remember the risk assessments, the risk assessment will usually create or output, as part of the formula that you work through, a required performance level given the risks that you have, small risks or large risks. And then you combine that with the system architecture, which are the category B, category 1, category 2, the previous slides. And then your system architecture plus the MTTFD, this mean time to dangerous failure, with the parts that you have in your system architecture. So you must have a good system architecture and good parts. And then when you combine that, you're able to say that you need this PLR for your system to be safe, and your safety system has a certain PL. And you compare the two. This sounds simple. The challenge is that first, now you need to do this for every single risk. And then you need to convince the people who are funding the project to make sure that you can afford all of the sensors to cover this with every single risk. So there is a significant challenge. The nice thing is that these are standards and they are known terms. So when you say PLR or MTTFD to someone in Japan or in Canada or in Germany, they will probably all know the same numbers. These are standard terms. I know I said you can't fully test everything for millions of hours, but I think it is also important to look at the 4 different key types of software testing. The first, and the reason for that is that there should be a balance between all of these types of software testing or all of these types of system testing. The first is traditional, what is called V-model development. Here, you lay out your various specifications, and as you move through development, you build various test plans against each of these specifications at various levels. Part of this is then enhanced by automated unit testing, as an example. I'm sure many are familiar with automated unit testing. It makes V-model development possible with the complexity of robot systems. Then you have simulations, dynamic simulations. This is Gazebo, which Louise will be speaking on, and I'm sure some others will be speaking on later today. This is part of our automated testing. For example, with the ClearPath autonomous systems, every time we put new code into our build systems, it runs unit tests and simulations. It will not produce a good output unless the simulations have also been passed. This really helps both speed your testing, and it also means you do not need to buy nearly as many robots and as much space for all the robots to run. And then the final point is you must always do some amount of real-world testing. Sometimes this is for safety. This helps you find those low probability, high impact events. But also, just from a practical perspective, it's very important to understand where some surprises may come in. And this is a challenge when you're building your company or as you're building your team, is to find the right balance between every one of these 4 points. Because if you focus too much on one of these sections, you will probably make some mistakes or miss some discoveries. Now, to conclude, the 8 points here that we went through, just to provide some very, very high-level points. First, safety. Safety is being more cautious than people, but still not being perfectly polite. When it comes to the environment, ask yourself, first and foremost, how foolish are the people working with your robots and around your robots? When it comes to the rules and regulations, they are very good to understand, but you'll probably need to ask first principles questions, basic questions about the way your robots will work. When it comes to risk, really look for these low likelihood, high impact risk. In terms of the mitigations, intrinsic safety is best. But in many of the robots you will be building, you will have to use some sort of functional safety. When it comes to designing safety, keep things as slow and light as possible if you can, and to have stopping methods, like emergency stops, even when you are testing your systems. As we come to architecture, really understand the need for redundancy and determinism in your architecture and in your designs. And then finally, when it comes to the statistics, you don't want to trust your eyes or your feelings with the robot. You don't want to trust the fact that you've seen the robot work for a day or a week or a month. You want to really look at the statistics and make sure that you are not too enthusiastic about it. The statistics are what will make the difference when it comes to safe operation in the world. Thank you very much for your time. I believe there is some time for questions.
ライアンさん、基調講演ありがとうございました。それでは、10時5分まで質問の時間にしたいと思います。ぜひ挙手お願いします。日本語でも結構です。
I believe I'm just getting an earpiece.
あちらの会場、向かって左側。
Well-organized open source community in the software world, thanks to the open robotics. Would you have any opinion about a benefit of using ROS as a basis of your product, where the safety really matters?
I believe the question was how comfortable would we be in using ROS for safety? Is that a good way to put it? And thank you very much for your kind words in general on behalf of both ClearPath and Open Robotics. It's important when you're a good thing to look at when you're using ROS for safety, or if you're considering using ROS for safety, is can it do all of these points? Or can an area like this logic be implemented in ROS? And there are details there. For example, is ROS being run on regular Ubuntu, or is it being run on a real-time kernel, as an example? The other detail could be what happens if ROS fails. This is another emergency, this is another risk assessment point, because all software fails. And that also takes into account the robot you are building. If you are building a small robot which does not cause, which won't cause injury if it comes to a complete stop, then it's easier to use ROS than if you are building an airplane, for example, where if ROS comes to a complete stop, it also creates a safety hazard. But the simple answer is that we don't presently we use ROS at the vehicle dynamics management level and up. So the safety rated subsystems and 1/2 of vehicle dynamics management do not use ROS. They use well-tried safety rated systems. But we have started to look at where ROS can be used in some of these areas, and we are very, very enthusiastic to see the amount of support from the automotive community in helping move towards more predictable behavior in ROS.
もう一方質問されたい方いらっしゃいますか？では会場奥後方の方にお願いします。
Good morning, David from CEOs. We're building robots at the moment. I just have a question about the intrinsic safety that you mentioned. You mentioned that the robot is intrinsic safe when the speed is less than 0.3 meters per second or less than 100 kilograms of mass exactly. Would you say that a vehicle, an AGV that is about 80 plus kilograms of mass would be intrinsic safe when it can actually cause pretty bad harm if hits you in the leg, for example?
If it can cause you bad harm when it hits you in the leg, then no, it is not intrinsically safe. But usually the reason, when I use the phrase total mass, it's because of the mass of the vehicle and the payload. So if your AGV is at 80 kilos and it's moving at speed, it's probably okay. But you would find that when you take in an 80 kilo AGV, you can probably put another 100 or 200 kilos on top of the AGV, and now you're talking about a 300 kilo mass that's moving, which is well outside this boundary. That's like a fully loaded refrigerator.
Yes, but how about the shape of the AGV when you have sharp corners?
This is the details, right? If you have a soft, round robot, then you can move faster or have a heavier robot. But if you have a smaller but sharper robot with sharper edges, then you'll need to decrease these numbers. This is meant as a general guideline. We have seen many companies who they build a large vehicle, for example, that will mass 100 or 200 or 300 kilos, and then they ignore safety. So it's meant as a guideline, but yes, you're very correct that if you have a small robot and a light or slow-moving robot, but it has sharp edges, then you will need to. It is no longer intrinsically safe.
Thank you very much.
それでは時間になりましたので、残りの質問に関しては、休み時間などを利用して皆さんライアンさんにアプローチしてみてください。5分遅れで進んでおります。それで、次は清水さんによるウィルの発表に移らせていただきます。